This is Team 15, and this is our final video for the drill press. Our team includes Yuri, Daniel, Andrew, Caleb, and Nick. The benchtop drill press is a powerful tool designed to bore holes in a variety of materials using different types of bits to create different size holes. It's designed to have a relatively small footprint while being able to drill accurately placed holes. Some of the common components found on the drill press include a cast iron base, an adjustable table, and an aluminum or polycarbonate top cover. Here's an exploded CAD view of the drill press, which shows the 6 sub-assemblies that make up the drill press. These include the base, column, table, head, pulley box, and spindle assembly. There are a total of 23 components, excluding fasteners, that make up this machine and its sub-assemblies. Our primary customers we are targeting are manufacturing shops, which make up 2/3 of our production volume. This group is looking for a versatile machine that can handle a wide size range of materials and can create accurate holes with the option of mounting the machine. Our secondary customers, who take up the remaining 1/3 of our total volume, are educators and hobbyists who are looking for a machine that has a small footprint but is more accurate than a traditional handheld drill. Along with this, they want a machine that's easy and safe to use. We did a functional analysis using a FAST diagram and concluded that our task function is to drill a hole and that our primary basic functions are to spin and press the bit and fix the position of the workpiece. The support function that is most relevant to the drill press that needs to be focused on is creating a dependable design.
There are 2 sequences for our assembly plan, and when you compare them, the right side sequence is better than the left, with an advantage of testing sub-assemblies.
The head subassembly has a large assembly time due to the number of components and fasteners. It also has a significant amount of unnecessary components as seen in the mapping matrix. This made it an ideal component to redesign for manual assembly. This is the cost of manual assembly before redesign. It is shown on the table that the number of fasteners increased the assembly cost significantly. Our redesign could reduce assembly costs greatly by removing them. Here we see the before and after images of the redesigned head assembly. The images in the middle show 3 design guidelines used to redesign the part. First, we reduced fastener count by combining the end caps of the feed handle with the head body. This removed 12 bolts from the assembly. Another guideline used was adding features to guide the motor. A lip was put in to guide the motor to the holes needed to secure it to the body. Finally, we reduced part variety by making the few required fasteners the same. All the bolts are now M10 instead of a variety of sizes. The redesigned head assembly, as seen in the red, has a significantly cheaper assembly cost of 88 cents. This was due to reducing fasteners and making access easier. The redesigned head also combined the pulley subassembly as it no longer needed a separate enclosure. This required a small redesign in the module to make it compatible with the new head assembly. Here's the redesigned larger pulley module. The small pulley wheels still fit on the motor without modification, but the larger pulley needed a slight change. The changes removed several parts and reduced assembly cost. A flange was added to the spindle shaft for grip, and then the top was hammered to remove the need for a bolt holding it in place. The bushing was replaced by machining the shaft to higher tolerances. These changes to the pulley assembly module cut the cost in half.
Next, we took a look at the opportunities for redesigning the pulley box subassembly for automated assembly. These parts serve to prevent injury and protect the user from the moving belts and pulleys, which transfer the power between the motor and the spindle. The quad chart here shows there is high opportunity for redesigning the box itself, as it has a high manufacturing cost and importance. The handling and insertion cost of each part was calculated and shown here for automated assembly. At an assumed rate of 60 pulley boxes produced per hour, the assembly costs were 15 cents per part. The goal for this redesign was to reduce the assembly cost by reducing the number of parts which were assembled. Was once a 14-part subassembly was reduced to a single part, therefore reducing the assembly cost completely to 0 cents per part for this subassembly. The function of the pulley box itself was reimagined to serve more as of a lid rather than a clamshell box. The bottom flat surface of the piece was eliminated, as the redesigned head box provides needed rigidity rather than with that piece. This, along with a snap fit connection, allows easy removal of the lid by the user to change gear speeds while maintaining the safe function. Looking on to selecting a candidate process for the redesigned pulley box, the mechanical fit of the lid was deemed the most critical dimension. A main factor in determining the quality of the fit is the position of the snap fit tabs. If the tabs cannot align, the lid cannot be placed on. A positional tolerance of plus or minus 1.0 millimeters was determined to be reasonable for a number of candidate processes, given the size of this part. In addition, there will be some wiggle room designed into this tab mating hole and on the tab itself to act as an alignment aid. Finally, we narrowed down the candidate processes based on the process capability attributes. The material should be a thermoplastic or a non-ferrous metal. Next up, the shape of this part is a non-circular prismatic part, which could be cast or molded, or it could also be considered a flat sheet part, which could then be formed or machined. The order quantity of 50,000 parts meant this process needed to be very robust. And overall, this led to there being two candidate processes, which were injection molding and sheet metal forming. Sheet metal forming was chosen in order to satisfy the primary customer requirements of this being a durable machine that can withstand the environment.
The size of the new head box is 550 times 250 times 365. So because of its size, some other dimensions are not much important to operate. But the head box is directly related to tensile motion between pulley and the spindle. Tolerance of the bottom hole is much important. We set the size tolerance for this hole as plus minus 0.5 millimeter, which is motion is not disturbed by the frictional misalignment. Also, the hole has 2 millimeter of gap to keep for preventing other unexpected inefficiency of motion. The process of a head box is determined by several criteria from its properties. The material head box is non-ferrous metal. It has no circular prismatic shape. It is 8.4 kilogram. Section thickness is 2 millimeter. Given tolerance is plus 0.5 millimeter. Surface finishing is not critical, and economic batch size is around 15,000. From these values, available options are die casting, sheet metal forming, and machining. So we select the die casting because die casting is the best option to satisfy the given requirement on our project. There was total 14 components include fastener on our old design. By eliminating the fastener and some holes from the old design using DfM 2 and 11, we can effectively decrease the number of the setups and can avoid narrow feature at the side wall of the old design. Eject the hole for the hinges. This is designed for the head box. By adding extrude cut near the lips, we can keep uniform mold thickness, so it can decrease the cycle time. By decreasing the lip thickness, we can decrease the material cost and prevent sink. Furthermore, the original design was covered by the top, but the new design is open, so it will be avoid the internal depressions and will decrease the die cost. When we put our new pulley box design in the hubs, it doesn't give us unit and total price because of its shape. But from the lecture 10, it was 25 expensive than the calculated cost. So we can expect the cost for our model will be the $1.67 per part. Also, when the base size is increased, the cost will be decreased to calculate cost $1.33 per the part.
We did a cost analysis of the machine for the original design, as well as the redesigns of that motor head box and the pulley. The original price of the motor head box was a little over $66. When it was redesigned, it increased to $72.24 because of the increase in overall raw material, as well as more machines being used to create it. The original pulley consisted only of purchased parts, which is why it had a $0 machining cost. But the new pulley system is all machined and it costs $22.34. For hardware like a drill press, the main importance is upkeep of the drill press. So we decided that we'd create a website for customer service to buy replacement parts, and also a chance to purchase a subscription for a maintenance kit, which would have monthly cleaning supplies and lubrication supplies. The new design allows for a reduction in weight well as allows the customer to choose the platform that is best for them. It is less durable but easier to manufacture. If we were to restart, the group would focus more on minimizing the number of parts used to lower machining time and total cost. We could also redesign the base and table subassemblies.